Everyone. I hope that you are doing well. My name is Professor Andrew Timming, and I'm very pleased to welcome you to this second lecture corresponding to Chapter 5 of my textbook, Applied Statistics, Business and Management Research. So in this lecture, we will calculate an independent samples t-test. In other words, we will do this by hand, in other words, doing the math. And then we'll also learn how to interpret the results of an independent samples t-test. Now, the reason I'm asking you to calculate a t-test by hand is that I think it's important when learning statistics that you don't over-rely on the statistical software that will do the math for you. SPSS will clearly do all these calculations for you simply at the click of a button. You just click OK and it will give you the results. But in my view, in order to fully grasp data science, it's important to have some, even if it's vague, some understanding of what's going on mathematically when you ask a statistical software program to carry out a statistical test for you. So we'll focus in the first part of this lecture on calculating a t-statistic, which is the key statistic that speaks to the generalizability of the results of your t-test. And then in the second, we'll look at using SPSS to carry out an independent samples t-test. All right, let's begin. Okay, so here is the textbook that we are using in this lecture series. It's called Applied Statistics, Business and Management Research. It's a textbook that I wrote. And the lecture that we are going through today at this moment corresponds to Chapter 5 of this textbook, which looks at the calculation and logic underlying the t-test. So without further ado, how about we jump right into calculating a t-statistic. Let's look at the underlying mathematical mechanism briefly before we jump into a tutorial on how to carry out an independent samples t-test using SPSS. Now, this equation in front of you might appear at first glance to be somewhat intimidating because there is a lot apparently going on here. But if you break this equation down into its constituent parts, it becomes much easier to understand. So recall, what we're trying to do here is to calculate the t-statistic, which says something about the extent of the difference in mean scores across two groups, right? So this is the logic of the independent samples t-test, is you're taking Group A and Group B, you're looking at a particular outcome, a particular dependent variable, and you're asking whether or not the mean differences that you found in your sample generalize to your population. And the question of whether or not these mean differences generalize depends on the magnitude of your t-statistic, where the larger the t-statistic, the more likely it is that your results generalize to the wider population. There are a couple different equations that we use to calculate t. This is an equation that we use for small samples. So let's have a look at the different parts here. So we have t equals, and then at the top we have the mean, so that's x bar of group 1 minus the mean x bar of group 2. So we're taking the mean of one group and subtracting it by the mean of another group, and then we're dividing that by the square root of, and then you can see N1, so we have the number of cases in group 1, N2 is the number of cases in group 2, and then S sub 1 squared, we have the standard deviation of group 1, S sub 2 squared is the standard deviation of group 2, and then we multiply that by the square root of the number of cases in group 1 plus the number of cases in group 2 divided by the number of cases in group 1 times the number of cases in group 2. So again, apparently there's lots going on here, but if you break this up into its constituent parts, as we will do over the next few slides, it is much easier to understand. So let's look at our data here. This is hypothetical data. In other words, these aren't real scores. I just sort of put them together in order to illustrate how to calculate a t-statistic. And this is actually going to be quite an easy one to do, and I'll explain why that's the case. So we have 12 participants here, so we know our sample size, our total sample size is 12. And then our independent variable here is whether or not the participant has a tattoo. So a 0 indicates no, there's no tattoo, and a 1 indicates yes, this person has a tattoo. And then our outcome variable is a performance score. So you can see there are a number of scores there. It looks like we have a low of 2 and a high of 4, and then a few 3s thrown in there. So we have two groups, tattooed versus non-tattooed, and each group consists of 6 participants. And what we're trying to do is to look at whether or not tattooed people or employees differ from non-tattooed employees in relation to their performance appraisal scores. So using these data, how would we go about and calculate the t-statistic from the equation in the previous slide? Let's have a look. All right, first thing we need to do is to calculate the mean performance score for our group 1. Our group 1 is individuals or employees with no tattoo. So their performance appraisal scores were 2, 3, 2, 4, 2, and 3. And if we add all these scores up, we get 16. And if we divide by 6, we get 16 divided by 6. In other words, group 1 has a mean performance score of 2.67, right? So 2.67 average performance for employees without a tattoo. Right, the next thing we need to do is to calculate the average or mean performance score for our second group, and our second group consists of employees with a tattoo. So these employees have performance scores of 3, 2, 4, 2, 3, and 2. And if we add all of these up, once again we get 16, and there are 6 scores in this set. So we divide that by 6, and we get an average performance score for those with a tattoo of 2.67. Now you'll recall that this 2.67 is exactly the same mean score as in group 1. In other words, group 1 has a mean performance score of 2.67, and group 2 has a mean performance score of 2.67. In other words, the performance scores are identical. So we already know before actually calculating this t-statistic that the result has to be 0. And the reason the result has to be 0 is that there is no mean difference between group 1 and group 2. It is the exact same number. So we know that this is going to be the case. We know that there's going to be no difference in mean scores because we can already see it based on just simple calculations of the means. But let's plug in all of the values just for fun, and again, to contribute to your understanding of statistics, knowing full well in advance that we already know what the result is going to be because there is no difference in the sample. Because there's no difference in the sample, there's no difference in the population as far as we are concerned here. All right, the next thing we're doing here is to calculate the standard deviation of performance for group 1. That would be the group of employees without a tattoo, and you can clearly see how we do this here. So we take the square root of each score summated and squared divided by 6 minus 2.67 squared, which gives you the square root of 46 divided by 6 minus 7.13, which essentially gives you the square root of 0.54 So the standard deviation in this case is 0.73. Okay, now we need to calculate the standard deviation for our second group. So this is the standard deviation for our employees with a tattoo. We already know the mean, as I said before, but now we're calculating the standard deviation for that second group. So we have the square root of each individual score squared added up divided by 6 minus 2.67 squared. So that again corresponds to 46 divided by 6 minus 7.13, which corresponds to the square root of 0.54, which gives you a standard deviation of 0.73 again. So we not only have the same exact mean scores across group 1 and group 2, but we also have the exact same standard deviations corresponding to each of those mean scores. So in both cases, the standard deviation is 0.73. Now that we know the results of the mean scores and the standard deviations, we can simply plug those into the t-test equation. So let's do that now. Again, knowing full well that the result is going to be t equals 0 because there is no difference in mean scores across the two groups. So just plug in the values here. We have, once again, to review, the mean of group 1, 2.67, and the mean of group 2, also 2.67. And we have the standard deviation of group 1 as 0.73 and the standard deviation of group 2 as 0.73. So to calculate t, using the equation that we looked at previously, we simply take our two mean scores across the groups and subtract them from one another. So 2.67 minus 2.67, which of course gives you a score of 0. And then you plug in the scores at the bottom half of that equation. So the square root of 6 times 0.73, so 6 is the number of cases in group 1, times 0.73 plus 6 times 0.73, so that's the number of cases in group 2, times the standard deviation in group 2, divided by 6 plus 6 minus 2 times the square root of 6 plus 6 divided by 6 times 6. So if you carry all these calculations to fruition, you will get, as we've already discussed, a result of t equals 0. So how do we interpret that? We would conclude that there is no difference in employee performance between employees with a tattoo and employees without a tattoo. All right, so let's look at another data set and we will see if we can carry out the same calculations. So we're going to also calculate t by hand. But in this case, I'm giving you an example where you will indeed find a mean difference between group 1 and group 2. And the key question at hand is whether or not that difference is large enough to generalize to the wider population. So in this case, we have, let's see, 14 participants. In the previous sample, we had only 12, and now we have 14. And so we have two groups now. We have our Ivy League degree variable, which is a nominal two-category variable. So a score of 0 means that the employee does not have an Ivy League degree, and a score of 1 indicates that the employee does have an Ivy League degree. And we're also looking at performance scores. So these are slightly different from the previous example. Here you can see we have a few performance scores of 9, and we have a low of, it looks like, 2. So maybe it's a performance scale of 1 to 10, let's say. And the question we're asking is, do Ivy League degree holders score higher on performance than non-Ivy League degree holders? And we have now two separate independent samples, each consisting of 7 participants. 7 plus 7 is 14. So I'd ask you at this stage to press pause and see if you can calculate the results of this t-test in groups or by yourself and come up with the correct answer. Okay, if you did your calculations on the previous slide correctly, you should get a t-statistic of 4.93, and you should further discover that in this particular data set, the average performance scores of individuals without an Ivy League degree are higher, much higher in fact, than average performance scores of those with an Ivy League degree. Bearing in mind, of course, these are hypothetical data. Okay, if you didn't get those results, then I would urge you to stop and redo your calculations. If you did get those results, then awesome, congratulations. Let's continue with today's lecture. So you've done a series of calculations of t-statistics by hand, and these are very small data sets. So the first data set that we did by hand had 12 respondents or participants in it, and the second had 14. And it's reasonable to calculate the results by hand when you're dealing with data sets that are so small. But if you're dealing with huge data sets with hundreds or maybe even thousands of participants, it would be unreasonable to expect someone to calculate a t-statistic by hand. So we are instead going to allow SPSS to do the work for us. So let's look at the various steps we can take when we ask SPSS to carry out an independent samples t-test. First thing you want to do is look at the descriptive statistics and the frequency distributions of both the independent and the dependent variables separately. So you want to do this first before carrying out the tests. The next thing is, in order to carry out the tests, you need to assign numbers to each of your two groups. So you define groups of the independent variable as either group 1 equals 1 and group 2 equals 2, or more commonly, you would define group 1 as 0 and group 2 as 1. So when you actually request the test be carried out and you look at the output window, what you're going to do is to compare the mean scores across the two groups and standard deviations. You're going to look for a Levene's test for equality of variance. You'll recall that we talked about one of the assumptions of the independent samples t-test is that the distributions across the two groups have roughly equal spread of scores, roughly equal variances. So you request a Levene's test that will tell you whether or not you have achieved equality of variance. And in this particular case, what you want to find with your Levene's test is a non-significant p-value. That is to say, a p-value that is greater than 0.05. Then, of course, you'll have the t-statistic itself and the p-value. The p-value will tell you whether or not the result, the difference that you found in your sample, generalizes to the population. You can also request or calculate by hand your own effect sizes, and the most common effect size is what we call Cohens D. So a p-value will tell you whether or not your result generalizes, but it won't say how strong the effect of your independent variable is on your dependent variable. To get a sense of the strength of the effect, we ask for or calculate a statistic called Cohens D. So the effect size reflected in Cohens D speaks to the strength of the effect of X on Y. So the larger the Cohens D, the greater the effect, the stronger the effect. Now, if you're using SPSS 27 or above, you can ask SPSS to calculate Cohens D for you in the output. If you're not, if you're using it at SPSS 20 below SPSS 27, then you'll have to calculate it by hand. So here's a general rule of thumb. A Cohens D of 0.2 represents a small effect size. If you get a Cohens D of around 0.5, that's a medium effect size. If your Cohens D is 0.8, that represents a large effect size, and a Cohens D above 1.2 represents a huge effect size. As I said before, the focus of this chapter in this lecture series is on the independent samples t-test, and this is where you compare mean scores across two separate groups. So you're almost taking two mini samples within your sample and looking at whether or not the groups differ in relation to the average score of a particular outcome. There's also a related or sister method called the paired sample t-test, which I've alluded to. And the paired sample t-test compares two mean scores across different points in time. So it's referred to as a repeated measure. So you have one group, you calculate their average at point in time 1, and then at point in time 2, you recalculate the average to see whether or not there is a difference between the 2 points in time. Right? So you have time 1 and time 2. As I said, these are quite common tests for psychologists, and the reason is you might have a sample, you calculate a mean score, whatever that might be at time 1, and then between time 1 and time 2, you implement some kind of intervention to see whether or not the intervention has an effect on the mean score at time 2. Like the independent samples t-test, the paired sample t-test also yields a t-statistic and a corresponding p-value that tells you something about the extent to which your results can be generalized from the sample to a population. All right, let's summarize what you've learned so far in Chapter 5. You've learned about the independent sample t-test, and the independent samples t-test compares mean scores across two independent groups. And as I said, we often code these as 0 and 1. In an independent samples t-test, the independent variable must be nominal with only two categories. So if you have more than two categories, we can't use this test. And the dependent variable, the outcome variable, has to be either ordinal or preferably scale. And the reason it has to be ordinal or scale, in other words hierarchical, is that we need or prefer to have the distribution look roughly equal. The test itself asks whether the mean scores across the two groups are significantly different from one another in the population, and the question of whether or not they're different will depend on whether the p-value for that test is less than 0.05. If it is less than 0.05, then we conclude that the result is statistically significant and that we can generalize from the sample to a population. Similarly, as we just looked at, the paired sample t-test is based on repeated measures at time 1 and then at time 2 within the same group of respondents. And again, we're looking at whether or not those two mean scores from time 1 to time 2 are statistically different from one another. Okay, at this stage, I would like you to pause and see if you can answer these 6 questions either in groups or on your own. Answering these questions will help you improve your knowledge retention of the material that you've learned not only in the last couple lectures, but also in your reading of Chapter 5 of the book. Thanks very much, everyone, for bearing with me. I look forward to seeing you soon. Take it easy, everyone. Bye.